Welcome to ReneEnergy.com, your renewable energy and sustainability platform. At ReneEnergy.com, we believe in the power of clean, sustainable energy to transform the way we live and work. That's why we offer a range of solutions for businesses and homeowners looking to switch to renewable energy sources such as solar, wind, and water. Welcome to this comprehensive guide on the future of green hydrogen. This presentation is brought to you by ReneEnergy.com, your go-to platform for all things renewable energy and sustainability. Today, we explore how technological advancements and falling costs are making green hydrogen an increasingly viable option in the sustainable energy landscape. Why is now the right time to delve into this topic? With remarkable progress in electrolyzer technology and declining costs of electricity from renewable sources, green hydrogen is more achievable than ever. It promises not just a cleaner world but also a host of new opportunities for innovation and investment in the renewable energy sector. In this presentation, we will walk you through the historical milestones in hydrogen technologies, crucial developments in electrolyzer designs, how economies of scale and automated processes are reducing production costs, the decreasing costs of electricity and their implications for green hydrogen, assessing the readiness level of different hydrogen technologies for scaling up, key performance indicators shaping the future of the industry. So let's begin this exciting journey into the world of green hydrogen, understanding its current state, its future, and why it matters to all of us. Historical context, understanding the roots to shape the future. In the last century, hydrogen has undergone multiple shifts in perception, from being seen as an industrial feedstock to its emerging role as a versatile energy carrier. But it hasn't been a smooth ride. There have been numerous challenges and setbacks. The evolution of hydrogen technologies. Hydrogen production initially relied on steam methane reforming, a method that is efficient but relies on fossil fuels. The quest for clean hydrogen led to the development of electrolysers, initially alkaline-based. While these were groundbreaking at the time, they were plagued by low efficiency and scalability issues. In the late 20th century, researchers turned their attention to PEM, proton exchange membrane, and EM, anion exchange membrane, electrolysers. PEM electrolysers offered higher efficiencies and a more compact design, making them ideal for integration with renewable energy sources. However, initial iterations were costly, primarily due to the use of expensive materials like platinum. Fast forward to today, and we have PEM and EM electrolysers that are not only efficient but also increasingly affordable due to advances in material sciences. New catalysts and membrane materials are reducing the need for precious metals, which in turn lowers the costs. Previous limitations, barriers to mainstream adoption. The journey has been far from smooth. One of the most significant barriers has been the high capital costs associated with hydrogen technologies. Early electrolysers, hydrogen fuel cells, and storage systems were prohibitively expensive for widespread adoption. Moreover, inefficiencies in electricity to hydrogen conversion meant that large amounts of electricity were needed, further raising operational costs. The challenges also extended to storage and transportation. Hydrogen has a low energy density by volume, which posed logistical challenges. Early storage systems relied on high-pressure tanks or cryogenic temperatures, adding another layer of complexity and cost. However, constant innovation has started to knock down these barriers one by one. Advancements in materials science have led to more efficient and cheaper catalysts. Improved design and manufacturing techniques are making systems more robust and scalable. Research into novel storage methods is also gaining momentum, aiming to make hydrogen as easy to store and transport as conventional fuels. Electrolyzer design and construction, the building blocks of a hydrogen economy. Hydrogen production through electrolysis is a fascinating interplay of science, engineering, and economics. Understanding the intricacies of electrolyzer design is key to scaling up the hydrogen economy. This section delves into how these systems are built and optimized. Impact of increased module size. Size matters in electrolyzer construction, especially in terms of efficiency and cost. Traditionally, electrolysers were built on a small scale, suitable for lab experiments or niche applications. But as the demand for green hydrogen surges, so does the need for larger electrolysers that can handle industrial levels of production. Increasing the module size of an electrolyzer leads to several benefits. First, it improves the system's overall efficiency due to better heat management and fewer losses. Second, a larger scale generally equates to a lower per unit cost of hydrogen produced, thanks to economies of scale. However, increasing size isn't without its challenges. Engineering difficulties, such as material stresses and the complexities of fluid dynamics, have to be overcome to successfully scale up. Variability in stack design. Electrolyzer stacks are the heart of the system, where water is split into hydrogen and oxygen. There's no one-size-fits-all design for these stacks. Instead, they are highly tailored to meet specific needs. Whether it's the material of the membrane, the type of catalyst used, or the flow configuration, each design variable can significantly impact the efficiency and cost of the system. PEM electrolyzers, for example, often use a more complex stack design to manage the acidic environment within the cell but benefit from higher efficiencies and faster response times. Alkaline electrolyzers, on the other hand, have simpler stack designs and are less expensive but come with a trade-off in terms of efficiency and operational flexibility. The variability in stack design is both a challenge and an opportunity. While it requires a greater depth of expertise to optimize, it also provides more avenues for innovation. By continually experimenting with new materials and configurations, the industry is inching closer to developing the ideal electrolyzer, one that is not only efficient but also economically viable. In summary, electrolyzer design is far from trivial. The decisions made at the design stage have far-reaching consequences for the efficiency, scalability, and economics of hydrogen production. But with each passing year, advancements in design are pushing the boundaries of what's possible, setting the stage for a more sustainable and economically viable hydrogen economy. Economies of scale, the key to affordable green hydrogen. As the renewable energy sector shifts into higher gears, economies of scale become increasingly important for making green hydrogen a viable and affordable fuel. Economies of scale refer to the cost advantages obtained by increasing the scale of production. In the context of electrolyzers, the benefits of economies of scale are twofold: automation in manufacturing and a tipping point in PEM electrolyzer costs. Automated processes in manufacturing. Advancements in automation technologies have streamlined the manufacturing process of electrolyzer components, from stack assemblies to power electronics. Robots and automated assembly lines have not only sped up the production but have also reduced the likelihood of human errors. The result is a more reliable, consistent product that can be manufactured at a lower cost. This automation becomes particularly beneficial when the scale of production ramps up. Large orders of electrolyzers can be fulfilled faster and at a reduced cost per unit. Consequently, the upfront capital costs for setting up hydrogen production facilities drop, making green hydrogen an increasingly attractive option. The tipping point for PEM electrolyzers. The polymer electrolyte membrane, PEM, electrolyzers have long been viewed as the more expensive, yet more efficient, option for hydrogen production. However, as production scales up and manufacturing techniques improve, the cost of PEM electrolyzers is approaching a tipping point. Soon, they may become as affordable as their alkaline counterparts, while offering superior performance and operational flexibility. Reaching this tipping point would be a game changer. It would accelerate the adoption of PEM electrolyzers in sectors that require high-purity hydrogen, like fuel cells for vehicles or grid balancing applications. As a result, we could see a rapid increase in demand for green hydrogen, pushing us ever closer to a sustainable energy future. To sum up, economies of scale are integral to making green hydrogen production cost competitive. Through automation and the approaching tipping point in PEM electrolyzer costs, green hydrogen is steadily becoming more affordable, widening its range of potential applications and setting the stage for a cleaner, more sustainable world. Lowering electricity costs, the unseen driver of affordable green hydrogen. While economies of scale play a critical role in reducing the costs of green hydrogen production, it's equally important to consider the electricity costs that fuel these electrolyzers. Lowering electricity costs has a direct, substantial impact on making green hydrogen more affordable. Historical data on solar and wind electricity costs. Over the past decade, the cost of generating electricity from renewable sources like solar and wind has plummeted. In some regions, renewables are now the cheapest form of electricity available. For example, the levelized cost of electricity, LCOE, for solar has fallen by over 80% since 2010, making it an increasingly viable source for powering electrolyzers. The low cost of solar and wind electricity has multiple implications for green hydrogen production. Cheaper electricity directly translates to cheaper hydrogen, making the green variant competitive with gray or blue hydrogen, which rely on fossil fuels. Implications for green hydrogen. The falling costs of renewable electricity mean that electrolyzers can operate during periods of low electricity pricing, or even capitalize on excess renewable generation to produce hydrogen at minimal costs. This trend creates a virtuous cycle. As more renewable energy is fed into the grid, the overall cost of electricity may continue to decrease, further reducing the cost of green hydrogen production. Utilities and energy providers are now looking at hydrogen as a way to balance the grid, storing excess electricity generated during peak wind or solar output. This not only brings down electricity costs but also provides a revenue stream for green hydrogen, enhancing its economic viability. In summary, the decreasing costs of renewable electricity are a key factor in the affordability of green hydrogen. As solar and wind energy become more accessible and less expensive, the cost to produce green hydrogen decreases, making it an increasingly attractive option for various industries and applications. Technologies ready for scale-up, paving the way for mass adoption of green hydrogen. As we consider the economic landscape for green hydrogen, it's important to note that multiple component technologies are now mature enough to be scaled up, pushing the industry closer to mass adoption. Current status of component technologies. From electrolysers to storage solutions, several key technologies in the hydrogen ecosystem are reaching maturity. For instance, proton exchange membrane (PEM) electrolysers have seen significant technological advancements, making them more efficient and cheaper to manufacture. Similarly, storage technologies like metal hydrides and advanced composite cylinders have matured to the point where they are not only safe but also economically viable. Investment requirements. While the technologies are ready for scale-up, substantial investments are needed to move from pilot projects to commercial operations. These investments span infrastructure, research and development, and manufacturing capacity. Governments and private stakeholders are increasingly recognizing the potential of green hydrogen and are starting to allocate capital accordingly. Public and private investments are funneling into the sector to accelerate technology development and deployment. Various grants, subsidies, and tax incentives are being offered to incentivize the transition from fossil fuel-based hydrogen to green hydrogen. These financial mechanisms play a crucial role in further reducing the cost of green hydrogen production and distribution. To sum up, several key technologies integral to the green hydrogen production process are reaching a level of maturity that makes large-scale operations feasible. However, to realize the full potential of these technologies, significant investments are required. Through collaborative efforts from both the public and private sectors, green hydrogen can become a cornerstone in our quest for a sustainable energy future. Key performance indicators for electrolyzer technologies: understanding efficiency and scalability. In the rapidly evolving world of hydrogen production, measuring the efficiency and scalability of different electrolysers is crucial. Key performance indicators, KPIs, serve as vital metrics to evaluate and compare different technologies. PEM electrolysers. Proton exchange membrane (PEM) electrolysers are known for their high efficiency and rapid response time. These characteristics make them suitable for applications that require fast ramp-up and ramp-down cycles, often matching well with renewable energy sources like wind and solar. Key KPIs for PEM include electrical efficiency, lifespan, and operational flexibility. Recent advancements have also started to address the cost factor, making PEM electrolysers increasingly economical. Alkaline electrolysers. Alkaline electrolysers have been in use for decades and are well understood. They are generally cheaper but less efficient than PEM electrolysers. Key performance indicators for alkaline electrolysers include their ability to operate at high current densities and their durability over time. Despite their age, alkaline technologies continue to improve, particularly in terms of energy efficiency and material cost reduction. EM and solid oxide electrolysers. Anion exchange membrane (AEM) and solid oxide electrolysers represent newer technologies in the electrolyzer landscape. They offer a balance between the high efficiency of PEM and the lower costs associated with alkaline electrolysers. KPIs for these types include temperature flexibility, material durability, and long-term operational stability. In summary, understanding the key performance indicators for different types of electrolysers helps stakeholders make informed decisions. Each technology comes with its own set of advantages and challenges, but ongoing research and development promise to further enhance the efficiency, reduce costs, and increase the scalability of these crucial components in the green hydrogen ecosystem. Conclusion: the path forward for hydrogen technologies, where we go from here. As we have explored in this presentation, hydrogen stands at the forefront of renewable energy solutions, providing an increasingly cost-effective and sustainable way to store and transport energy. From understanding its historical context to diving deep into the specifics of electrolyzer design, economies of scale, and key performance indicators, it's clear that hydrogen technologies have evolved significantly over time. Summary of key points. We've seen how the costs associated with hydrogen production are declining, thanks to advancements in electrolyzer design and economies of scale. Lowering electricity costs through renewable sources like solar and wind further boosts the feasibility of green hydrogen as an energy carrier. Future outlook. The next frontier for hydrogen technology includes scaling up current component technologies and driving down costs even further. With the right investments, we're looking at a future where hydrogen not only complements existing renewable energy solutions but could become a dominant force in the global energy landscape. Research and development in electrolyzer technologies, especially PEM, alkaline, and newer designs like EM and solid oxide, will play a pivotal role in this transition. By continually improving efficiency, reducing costs, and meeting stringent performance metrics, hydrogen technologies are well on their way to being a cornerstone of a sustainable energy future. This concludes our presentation. Thank you for tuning in, and for those interested in renewable energy and sustainability, ReneEnergy.com is your go-to platform for more insightful content. Thank you for choosing ReneEnergy.com as your go-to source for all things renewable energy and sustainability. With our YouTube channel, we explore the latest developments and innovations in the field, including hydrogen fuel cells and the use of AI and machine learning to optimize energy consumption. If you're ready to take the next step towards a cleaner, more sustainable future, visit us at ReneEnergy.com and discover the many ways we can help you transition to renewable energy. Thank you for watching and subscribing. Stay up to date on all the latest news and insights by subscribing today.